you're back. I hope to talk about linear independence of matrix columns. All right, more fun facts. Yay! All right. We know that if we thought about each of these being a vector, so if this is vector 1, vector 2, vector 3, then we can talk about the linear independence of each of those columns. And those columns are linearly independent, again, if and only if the, notice this is the homogeneous matrix equation, so no longer vectors equation. It has, so it's linearly independent as long as that has only the trivial solution. So again, now we don't have to think about like setting up our vector equation and doing our x1 times v1 and x2 times v2 and x3 times v3 equaling 0, and then thinking about putting in the matrix and doing the augmented and blah, blah, blah. We can go straight to, hey, let's make an augmented matrix of this. 1, 2, 0, all right. 0, 0, 0. All right, pause it right now. You do the row reductions. Come back. See how you did. Look at all those beautiful row reductions. Now, honestly, we could have stopped here. Didn't have to go that extra step by doing the division. You'll also notice that I did a couple steps all in once. I switched my top 2 rows just so that I end up with a 1 in my top position. But honestly, all we're looking for here, again, to see if I have a trivial solution, if that's the only solution, I just need to see how many pivot points I have. If I have the same number of pivot points as I do my variables, then I'm linearly independent and I don't have to go any further. So if I can get it down to all ones in the diagonal, awesome. So you'll notice here that I have all pivot points here, so I have no free variables. So therefore, it's linearly independent, which can be helpful. That's going to help us with things in the future. But what that means is that I can't use any of the other 2 vectors to get the third vector if I think about those columns as being vectors. Now, again, I could have determined that same solution, that I could have gotten to that same conclusion by not going all the way to that REF form. Or I could stop at REF form instead of going that next step to get that 1, because this still shows me, if I just look at the leading entries, this still shows me that I have three pivot points. So honestly, you could stop either way. This one here is not enough to tell us that information, but once I can get down to that third matrix that I have here, then I have enough information to say that I have 3 pivot points, so I have no free variables, I'm linearly independent, they're not linear combinations of each other. There are 8 different ways to say the exact same thing here. Woohoo! Okay, so let's talk about my little fun fact here. We're going to go back to this idea of span now that we have a better understanding. So if 2 of my vectors are linearly independent, then that means that their span is a plane. So remember, we looked at that in a previous video, like, I don't know, for me it was like 10 minutes ago, for you, who knows. So their span is a plane. Okay, so 2 vectors, their span is always going to be a plane. Now it's going to go through 0, 0. If that third vector is within that plane, or is in the span, then it's in the plane. That means that they are all linearly dependent. Right? So if they're all within that plane, that means that I can take any 2 of these vectors and create any other vector within that plane. So if I make my plane a little bigger, I can make any other vector in that plane, which means they are all linear combinations of each other. If that third vector, though, is not in that span, so it doesn't lie in the plane, then we can say that they are all linearly independent. So what you can see here is that if I looked at the span of U and W, it's not the same as the span of U and V, right? So W is not in that span, so it's not within those linear combinations, or in other words, W U and V are not all linear combinations of each other. So this can be helpful for thinking about, so that's sort of what we just showed in that previous example, is that all of the columns, if I were to actually like graph the vectors for those three that represent the three columns in that matrix, none of them would all lie on the same plane. Now I could make, if you have two lines, you can always make a plane out of it, or two vectors always make a plane, and they make a unique plane. But it's when that third vector is in that plane, everything is linearly dependent. When that third vector is not in the plane, everything is not dependent, they're independent. All right, that's my 2 cents on linear dependence, independence. Oof.